Hello, everyone, and welcome to the CTAIO Labs podcast. I'm Thomas Promer, your host, founder of CTAIO.dev, the destination for future tech leadership. For anyone new here, I spent over 2 decades in tech as a hands-on developer, engineering manager, CTO, and CIO, inside companies like Apple, Google, Netflix, Adidas, and McDonald's. Today, I advise mostly Fortune 50 enterprises at that critical intersection of technology and AI to future-proof their businesses. On this podcast, we get hands-on, real, pragmatic, real-world lab experiments at exactly that intersection. To secure your weekly AI edge, subscribe to my newsletter at CTAIO.dev. That's where new episodes drop too. And if you'd like to say hi or ask about advisory work for your enterprise, head to promer.net. A response is always guaranteed. Now, this is the season 1 finale of Building My AI Twin. We've cloned my voice, then my face and body. Today, we clone the hardest part, my brain. My knowledge and my working memory. I ran a head-to-head, the same corpus, the same 7 hard questions, 3 competing architectures. And here's the spoiler right up front. A boring folder of plain text files beat the production-grade rack system I built myself. The entire brain experiment cost me $4.30. What follows is a deep dive generated with Notebook LM, based on the full lab report at CTAIO.dev. Easy listening for your commute, your run, wherever you are. I'll be back at the end to wrap it up. Enjoy.
So, imagine spending thousands of dollars and, weeks of engineering time to build the ultimate AI-powered second brain for your organization.
Oh, yeah, the dream of the digital Ferrari.
Exactly, the digital Ferrari. You deploy the latest production-grade retrieval architecture, you wire up the vector databases, you fine-tune the embedding models.
You do everything by the book.
Right. And then when you finally put it to the test, it gets absolutely demolished by a boring folder of plain text files from the 1970s.
Which is just such a brutal reality check, but that is exactly what happened to Thomas Promer.
It really is. So if you're tuning into this deep dive, you are likely someone tasked with making sense of the current artificial intelligence landscape.
Yeah, whether you're a CTO weighing enterprise architectures or maybe a head of AI engineering managing deployment budgets.
Or even just a developer trying to build a reliable personal knowledge system on your local machine, honestly. The experiment we are analyzing today cuts right through the noise of modern AI marketing.
It really does. And the broader context here is the grand finale of Thomas Promer's Season 1 project for CTAIO.dev. It's titled Building My AI Twin.
Right, which was this incredibly ambitious, systematic attempt to digitize a human professional.
Yeah, in Episode 1 of his journey, he tackled the audio layer, cloning his voice. Then in Episode 2, he built the visual layer, cloning his face and physical mannerisms for video avatars.
And today, we're looking at the final, most complex layer of that project, which is cloning his brain.
Yeah, we're talking about replicating his specific knowledge base, his retrieval mechanics, and his working memory.
Which is the holy grail, right? How do you take a professional's notes, corporate strategies, technical files, and actually build a system that can retrieve and process that information the way they would?
And the answer the industry wants to sell you right now is a highly complex, multi-layered AI pipeline.
Oh, absolutely. But Thomas decided to actually stress test that assumption. He didn't just build one system.
No, he built 3 entirely different architectural paradigms and pitted them against each other in a head-to-head battle.
With a very rigorous methodology, because to prove that a system works or fails, you have to control the variables.
Exactly. He established incredibly strict parameters for this benchmark.
And that control is what makes this specific deep dive so valuable for you listening, especially if you're an engineering leader.
Because the industry is, frankly, notoriously poor at benchmarking internal AI tools.
They really are. Often a team will test an architecture by, changing the underlying data, altering the prompt instructions, swapping out the models all at once.
Right. And then when a failure occurs, they have literally no idea which component broke.
Yeah, so Thomas held the corpus of data absolutely constant. He used one single unified data set containing all of his notes, project files, and strategies.
And he also locked down the queries. He designed a test battery consisting of exactly 7 identical questions.
He fired those 7 questions at the 3 different architectures and scored them objectively.
Head-to-head.
Yeah. But let me ask you this. Why is it so critical to hold the data and the questions as absolute constants? Because if I'm an engineer tweaking a system, my instinct is usually to massage the data to fit the tool.
Sure. But massaging the data completely obscures the fundamental mechanics of the retrieval architecture.
Oh, I see.
When you hold the corpus and the queries constant, you isolate the retrieval mechanism as the sole independent variable.
Okay, so we aren't testing whether the AI is smart enough to understand the text.
Exactly. We are testing whether the system can physically locate the correct text and deliver it to the reasoning engine intact.
It's kind of like a high-stakes cooking competition, right? It's like giving 3 different chefs the exact same ingredients and the exact same recipe, but giving one a state-of-the-art smart kitchen, one an industrial warehouse, and one a campfire.
That's a great analogy. Or if we think about it mechanically, it's like testing 3 different fuel injection systems on the exact same engine block, using the exact same fuel and the exact same load on a dynamometer.
Right.
If the engine knocks on system A but runs smooth on system B, you know definitively that the injection architecture is the variable at fault. You've eliminated data bias entirely.
Which is huge, because the knowledge itself is separate from the mechanism used to fetch it. I mean, storing facts is not the challenge in modern computing. Hard drives are practically free.
Yeah, storage is trivial.
The true measure of a second brain is the retrieval and synthesis of those facts under pressure.
Absolutely. If a system has indexed every document a company has produced in the last decade, but it cannot accurately pull the Q3 revenue numbers when the CEO asks a direct question,
then that system is functionally dead weight.
completely useless, yeah.
So let's look at the 3 contenders Thomas built to solve this retrieval problem. The first one is what he calls Ask CTAIO. This is his production RAG system.
Right, retrieval augmented generation. This is basically the absolute default architecture in enterprise AI today.
Yeah, if an organization is building an internal knowledge bot, they are almost certainly building a RAG pipeline.
Thomas built a custom Ask Tom framework specifically for this, which is actually currently live at ctl.dev.
I want to dig into the actual technical stack he used here, because it really represents the standard playbook you see everywhere.
It does.
He used OpenAI's text embedding 3 small model to create the embeddings. Those embeddings feed into sqlite-vec for the vector storage, and the final reasoning layer is powered by GPT 4.1 Mini.
Right.
Let's break that down for the listener. The embedding process is where the raw data gets translated. Like text embedding 3 small takes a piece of text, say a paragraph from a meeting summary, and converts it into a high-dimensional mathematical vector.
Exactly. It converts the semantic meaning of that text into an array of floating point numbers.
Yeah.
In the case of OpenAI's models, it might be 1,536 dimensions.
Which is wild to think about.
It is. And the theory behind RAG is rooted in geometric distance.
Okay, how so?
Well, when a user inputs a query, the system runs that query through the exact same embedding model, turning the question into a vector in that same 536-dimensional space.
Oh, I see. So it's mapping the question to the same math as the answers.
Exactly. The database in this case, sqlite-vec, then performs a mathematical operation, usually cosine similarity, to find the text vectors that are geographically closest to the query vector.
So it pulls those mathematically close chunks of text, hands them to the GPT 4.1 Mini model, and basically says, here's the relevant context, now answer the user's question.
That's the core loop, yeah.
It is an elegant concept. It maps meaning to math, but it's also a pretty heavy abstraction layer, isn't it?
It is a massive abstraction.
Okay.
Every time you translate human language into a mathematical representation of semantic meaning, you introduce a lossy compression.
Right, you're losing some of the literal nuance.
You are heavily relying on the embedding model's interpretation of what the text means. And we will see the consequences of that translation layer shortly.
Yeah, we definitely will. So that is Contender 1, the bespoke production-grade RAG pipeline. Now, Contender 2 takes an entirely different philosophical approach. This is Gemini 2.5 Pro utilizing a long context dump.
Yeah, this is just the brute force method.
There is zero retrieval architecture in this setup.
None. No vector databases, no embedding models, no cosine similarity calculations, no chunking strategies.
Wow.
Thomas basically took the entire corpus of data, an enormous 705,000 tokens, and pasted it directly into the Gemini model's context window, followed by the user query.
Just to visualize 705,000 tokens for you listening, we are talking about roughly 1 million words.
It's massive.
It's the equivalent of handing the AI several dozen dense technical textbooks simultaneously and asking it to hold all of that information in its short-term working memory while it processes a single question.
Which, historically, this architecture was physically impossible.
Really?
Oh, yeah. Early language models had context windows limited to maybe 2,000 or 4,000 tokens. The attention mechanism, the part of the neural network architecture that allows the model to weigh the relevance of different words against each other, scales quadratically.
Meaning the math gets impossibly hard the more text you add.
Exactly. As you increase the amount of text, The compute power required to process the relationships between all those words just explodes. But recent advancements have allowed models like Gemini 2.5 Pro to handle multi-million token windows.
Okay, so the theory here is essentially computationally aggressive laziness.
That's a funny way to put it, but yeah.
I mean, why spend weeks building a delicate retrieval pipeline to find the one right document when you can just force a massive supercomputer to read every single document your company owns every single time you ask a question?
Right, it trades architectural complexity for sheer computational brute force. You don't have to worry about an embedding model misunderstanding the semantic meaning of a query if the model simply reads the entire raw corpus in real time.
Which brings us to Contender 3. The file-based system powered by Claude Code, and this setup is shockingly Spartan.
Very Spartan.
We are talking about plain text markdown files sitting in a standard op directory on a local operating system. No databases, no vectors, no massive context windows.
Yeah, this approach is heavily inspired by Karpathy, one of the founding members of OpenAI. He frequently advocates for what he calls the LLM-OS, or LLM wiki concept.
Okay, so what's the engine here?
The core engine is Claude Code acting as an autonomous agent. But the crucial detail is the tooling this agent is given.
Right.
It is restricted to basic, fundamental computing utilities. It has a read tool, allowing it to open a specific file, and it has grep, the standard command line utility used in Unix and Linux systems for decades to search plain text datasets for lines matching a regular expression.
Wait, hold on. You're telling me Karpathy, a leading mind in artificial intelligence, is endorsing a method that effectively ignores the last 5 years of semantic search advancements?
I am.
How does a basic grep command handle synonyms? I mean, if I search for revenue, but the document says earnings, a RAG system using vector embeddings understands they mean the same thing mathematically. A grep command doesn't. It just fails.
That's true.
This seems like bringing a pocket knife to a laser battle.
I get why you'd say that. But that perceived weakness is actually its greatest structural advantage.
How so?
The grep utility does not understand synonyms, nor does it attempt to. It is purely literal. To understand the power of this, we really have to examine the failure modes of abstraction.
Okay, walk me through it.
Let's return to the RAG system. When text embedding 3 small maps a document into 1,536 dimensions, it is trying to capture semantic meaning. But enterprise knowledge is frequently non-semantic.
What do you mean by non-semantic?
It is often highly specific nomenclature. Alphanumeric part numbers, internal project code names, specific IP addresses, or exact API endpoints.
Oh, right. Things that don't have a meaning in the traditional sense, they just are what they are.
Exactly. A vector model might look at an API endpoint and try to map its meaning, placing it near other generic networking terms in the vector space, effectively losing the exact string of characters.
That sounds like a nightmare if you're trying to debug something.
It is. When a developer searches for a highly specific error code or a specific hexadecimal string, they do not want documents that are semantically similar to the error code. They want the exact literal match.
Right.
The RG abstraction layer often blurs specific details in its attempt to be universally semantic. The LLM wiki approach relies on foundational file systems. grep doesn't guess. It searches character for character.
Okay, but what if it misses?
The AI agent operates in a loop. It executes a grep search for a keyword, reads the standard output, and if it doesn't find the target, it revises its search string and runs grep again.
Oh, so it keeps trying based on literal text.
Yeah, it reduces the number of moving, opaque parts. It is the difference between translating a technical manual into interpretive dance and hoping you map the meaning correctly versus literally running your finger down the page looking for the exact spelling of a word.
Okay, that makes a lot of sense. So we have our 3 architectures, the sophisticated text embedding 3 small RAG pipeline, the 705,000 token brute force Gemini dump, and the simple folder of markdown files navigated by an agent with a grep command.
The stage is set.
7 identical queries evaluated head-to-head. Let's look at the actual outcomes. And remember, the setup he already had sitting around was those plain text files.
Right, the results of Thomas's benchmark are definitive. Let's start at the bottom of the scoreboard. Gemini 2.5 Pro, utilizing the massive long context dump, scored 1 win out of the 7 questions.
Ouch. A brutal showing for pure brute force.
Yeah, very rough. Next is Ask CTAIO, the custom-built production RG system, the architecture that represents the current enterprise standard. It secured 2 wins out of the 7 questions.
Wait, really? Meaning the system engineered specifically for this exact task failed on 5 of the 7 queries?
Exactly, which leaves the file-based system paired with Claude Code.
The basic markdown files.
It secured 5 wins out of the 7 questions. It absolutely dominated the benchmark.
Wow. I mean, if you look at the raw numbers, the overlap implies one question might have had a nuanced tie or multiple winners depending on the grading strictness, but the raw win count is undeniable. 5 for the markdown files, 2 for the production RA, 1 for the long context.
The simple non-abstracted architecture crushed the bespoke vector system. It wasn't even close.
It's like a reliable old Honda Civic beating a custom-built Ferrari in a cross-country race.
That's exactly what it is.
Yeah.
And it forces a real reevaluation of current engineering priorities.
Yeah.
Development teams are allocating millions of dollars right now to build complex vector databases, implement re-ranking models, and tweak chunking algorithms.
Yeah, it's a massive industry.
But this experiment suggests a massive degree of architectural bloat in the industry. Engineers are naturally drawn to complex, elegant-sounding mathematical solutions.
Sure, it's fun to build cool stuff.
But a plain text markdown file preserves the absolute integrity of the data. There is no chunking strategy to accidentally split a crucial paragraph in half. There is no embedding model to misinterpret the semantic weight of a critical part number.
The data just sits there waiting to be found. But before we dissect the failures, we have to address the single anomaly on this scoreboard.
The Gemini win.
Right. Gemini 2.5 Pro only won a single question, but the data shows it won the absolute hardest question of the entire battery, a question that both the RAG pipeline and the file-based agent completely failed to answer.
Yeah, and that single win reveals the one undeniable use case for the long context architecture. The brute force dump fails at general pinpoint retrieval, but it is entirely unmatched for hypercomplex, needle-in-a-haystack synthesis tasks.
Okay, define synthesis in the context of this specific benchmark. Why does grep or RAG fail here?
Well, a synthesis query doesn't ask for a single fact. It might ask the system to, say, identify the evolution of decision-making regarding budget allocations across the Q1, Q2, and Q3 strategy documents and compare that trajectory to the foundational mission statement drafted last year.
Oh, wow. Yeah, that's complicated.
A file-based agent using grep will fail catastrophically here. There is no single keyword to search for. The agent would have to run dozens of searches, read multiple massive documents, and try to hold all that context in its own scratchpad.
Which usually overwhelms the agentic loop.
Right. Exactly. It just loses the plot. And a RAG fails because of its fundamental design, chunking.
Because it breaks things up.
Right. When you build a RAG system, you don't embed entire books. You break the text into small chunks, maybe 500 tokens each. When you ask that massive synthesis question, the vector database retrieves the top 5 or 10 chunks that seem semantically related to budget allocations and mission statement.
But it fundamentally loses the global context.
Exactly. It cannot see the connective tissue between a subtle budget cut mentioned in a random Q1 Slack message and a major strategic pivot in Q3. It only sees the isolated fragments.
But Gemini, because it has all 705,000 tokens loaded directly into its working memory simultaneously, can run its attention mechanism across the entire corpus at once.
It sees the entire board. It can cross-reference the Q1 Slack message with the Q3 strategy document because both are currently active in its neural network.
So the long context dump is slow and computationally expensive. But for deep, sweeping synthesis across disparate documents, it remains the only viable architecture.
Exactly. The tool must match the specific cognitive task.
Okay, that makes sense. Now, winning the benchmark is only one metric. For enterprise deployment, understanding how a system fails is arguably more important than understanding how it succeeds.
Oh, absolutely.
We need to perform an autopsy on the specific failure modes of each paradigm. Let's start with the production RAG system. The failure mode here is what the sources call RAG confabulation, or the danger of fluency.
This is, without a doubt, the most critical risk for enterprise deployment. During the benchmark, the RAG system hallucinated an entire narrative. It completely fabricated a rumor about a company called ElevenLabs shutting down.
Wait, really?
Yes. And to be unequivocally clear, this ElevenLabs shutdown rumor does not exist anywhere in Thomas's corpus of notes, files, or strategies. The AI invented it out of whole cloth.
Okay, explain the mechanics of this hallucination to me. Because if a RAG system is designed specifically to pull factual context from a database and use only that context to answer the question, how does it end up lying? Where does the false information come from?
The vulnerability lies in the fundamental nature of the generative model at the end of the pipeline. GPT 4.1 Mini, like all large language models, is an advanced next token prediction engine.
Right.
It has been extensively fine-tuned through reinforcement learning from human feedback to be conversational, helpful, and, above all, fluent. It is heavily biased toward providing a smooth, coherent answer.
It wants to please the user by sounding confident.
Precisely. So when the retrieval phase of the RAG pipeline executes poorly, perhaps the vector database retrieves chunks of text that are only tangentially related to the user's query, the generative model is put in a really difficult position.
Because it has a user demanding an answer, but it only has a context window full of fragmented, unhelpful data.
Right. And instead of halting and stating the retrieved context does not contain the answer, the model attempts to bridge the semantic gap.
It tries to connect the dots even if there are no lines.
Exactly. It might see one retrieved chunk mentioning ElevenLabs in the context of voice cloning, and a completely unrelated chunk mentioning the shutdown of a different software project. The model's neural pathways interpolate between these concepts, stitching them together to form a highly fluent, grammatically perfect, and entirely false narrative.
Wow. So it optimizes for linguistic coherence over factual accuracy. In a business context, that behavior is just toxic. I mean, a confident lie buried in an otherwise accurate executive summary is far more dangerous than a system simply crashing.
That is the exact problem. And that leads directly to the second failure mode. This belongs to Gemini 2.5 Pro and the long context dump. This is the failure of budget exhaustion.
The specific event during the benchmark was that Gemini basically burned through its entire output budget while thinking about the more difficult questions and ultimately failed to provide an answer.
Right.
Let's break down the mechanics of an output budget for you listening. When I type a query into an LLM, what is actually happening regarding compute allocation?
Well, modern infrastructure requires hard limits. When you query a system like Gemini, you allocate a maximum number of tokens it is allowed to generate in its response.
Okay.
And this is not just the final text you read. It includes the hidden scratchpad space models used for chain of thought reasoning. Before delivering an answer, complex models will generate internal tokens to plan their response, execute intermediate logic, and cross-reference data.
They are essentially talking to themselves to work out the problem before speaking to the user.
Exactly. Now, the issue arises when you combine that chain of thought process with 705,000 tokens of raw input data. The attention mechanism of the model must calculate the relevance of every single token against every other token.
That sounds exhausting.
The computational effort required to navigate that massive sea of data is staggering. The model begins generating internal reasoning tokens, trying to map out a path to the answer. It pulls a thread here, cross-references a document there, gets confused by conflicting information in another file, and continues generating internal reasoning steps.
It just gets lost in the sheer volume of information.
It paralyzes itself. It spins its computational wheels so aggressively trying to parse the million words of context that it hits the hard limit of its output token budget before it ever arrives at a conclusive answer. It times out.
So the pure brute force architecture ultimately crushes the reasoning engine under the weight of its own data.
That's a great way to summarize it.
Which brings us to the third failure mode. The failure of the champion architecture. The file-based system powered by Claude Code failed a query due to a vocabulary mismatch.
Right, and this is a classic foundational computing failure. The agent utilized a case-sensitive grep command. It was searching the markdown files for a specific term. However, the formatting of the heading in the document used different capitalization than the agent's search query.
Oh no.
Because grep was executing a literal character-for-character search, it missed the target entirely.
So if the document says revenue with a lowercase r and the agent searches for revenue with a capital R, the system reports 0 results.
Exactly.
The rigid literalism that makes it accurate also makes it fragile to minor syntax variations. But the crucial differentiator here is the system's response to that failure, isn't it?
Absolutely. Unlike the RAG system, the file-based agent did not attempt to cover its tracks. It did not stitch together unrelated data to hallucinate a plausible answer.
It didn't invent an ElevenLabs shutdown.
No, it executed its search loop, failed to find the literal string, and simply returned to the user to report the failure. It flagged the miss. It honestly admitted it could not locate the information.
I want to pause on that file-based failure, because this requires a shift in perspective for anyone building these tools. As consumers of software, we are conditioned to view an I don't know, or a zero results found message as a poor user experience.
Yeah.
We want the technology to feel magical. But you are arguing that in an enterprise deployment, a system failing due to a rigid syntax error is functionally superior to a system providing a smooth, readable answer.
I will argue that point aggressively. In a high-stakes knowledge system, the hierarchy of value heavily penalizes false confidence. We must distinguish between a known unknown and an unknown unknown.
Okay, unpack that.
When the file-based system fails and says, I couldn't find that exact term, it creates a known unknown. The user experiences a moment of friction. They realize they might need to change their search parameters or manually open the file to check the heading. The human remains in the loop, aware of the system's limitation.
The friction acts as a cognitive guardrail.
Precisely. Conversely, ORAG confabulation creates an unknown unknown. The system delivers a polished paragraph detailing the shutdown of ElevenLabs. The user, assuming the highly expensive enterprise AI is retrieving factual data, accepts this premise.
Oh man, and then they drop that fact into a slide deck, present it to external stakeholders, or use it to inform a financial forecast.
Exactly. The cost of a known unknown is 3 seconds of user frustration. The cost of an unknown unknown can be catastrophic damage to a company's reputation or bottom line.
So the file-based architecture optimizes for ground truth accuracy and safe failure modes, completely sacrificing the illusion of omniscience.
That's it, exactly.
Okay, so that covers static knowledge retrieval. We have explored how these architectures fetch stored data. But a digital brain must also process dynamic data. It must manage a conversation. It has to remember the context of an ongoing interaction.
Right, the working memory.
Thomas tested this with a specific working memory probe.
The transition from static retrieval to dynamic context management exposes a completely different set of architectural flaws in modern AI systems. Thomas designed a 5-turn conversation test to stress the system's ability to retain and prioritize explicit instructions over time.
A conversation where the user and the AI go back and forth. Tell us the exact parameters of turn 1.
At the very beginning of the interaction, the user issues a hard, undeniable constraint. The command given to the system is, never include specific dollar figures in your responses.
Which is a foundational rule for the interaction. If I tell a financial analyst, we are discussing strategy today, do not mention the Q3 revenue numbers, I expect that rule to govern the entire meeting. What happened during the test?
The interaction proceeds normally for several turns. The user asks questions, the AI responds without using dollar figures, turn 2, turn 3, turn 4. The system appears to be functioning perfectly, but the catastrophic breakdown occurs at turn 5. The user asks the question about a specific project's scale, and the system completely ignores the foundational rule from turn 1. It returns an answer saturated with specific dollar figures.
It completely dumped the core constraint. It suffered total amnesia regarding the rules of engagement. What is the technical mechanism driving this failure? Why does an advanced AI simply forget an explicit command?
The amnesia is not a bug. It is a direct result of a highly common architectural optimization. Managing context windows is computationally expensive. To prevent an ongoing conversation from infinitely expanding the required compute power, system architects implement rolling history caps.
A rolling history cap.
Yeah, the system Thomas was testing utilizes a 6-message rolling buffer.
Meaning the system's working memory only contains the most recent 6 messages exchanged between the user and the AI.
Right, it acts as a sliding window. As the conversation progresses, new messages are added to the front of the queue, and the oldest messages are systematically dropped off the back. They're entirely erased from the model's active context.
Ah, I see.
Once the user and the AI execute enough conversational turns, that critical foundational instruction from turn 1 slides outside the 6-message window. The AI's working memory is wiped clean of the constraint.
The benchmark documentation explicitly labels this phenomenon Sphere's working memory gap.
Yeah.
It is the digital equivalent of hiring an executive assistant who takes meticulous notes, but systematically shreds the oldest page in their notepad every 5 minutes.
That is exactly what it's like.
If I'm a CTO trying to deploy an AI twin to act as a proxy for an executive, something I can delegate complex, multi-step tasks to, how crippling is Sphere's gap?
It fundamentally prevents true delegation. Human working memory does not operate as a simple first-in, first-out buffer. Human cognition involves the persistent prioritization of overarching rules.
Right.
If a manager tells an employee on Monday, never email the client list to external vendors, the manager expects that rule to remain active on Friday, regardless of how many other conversations have occurred in the interim. The rule has hierarchical weight.
But current rolling cap architectures treat all conversational turns as equally relevant, decaying their importance based purely on chronological time rather than structural importance.
Exactly. To build a functional AI twin that can operate autonomously, the architecture must separate core instructions from transient conversation. Foundational rules must be anchored in the system prompt or injected into a persistent memory module that bypasses the rolling history buffer entirely.
Which makes total sense.
Until that is standard practice, any AI system engaged in a long interaction will inevitably suffer from Sphere's gap and violate its operating constraints.
We have dismantled the architectures, analyzed the failure modes, and exposed the limitations of dynamic memory. Let's synthesize this data into actionable intelligence for the engineering leaders and builders listening today.
Let's do it.
Based on the hard data from Thomas's Season 1 finale, how should a CTO approach the decision matrix for an enterprise knowledge system? When do you pick which paradigm?
The core realization here is that the industry's default architecture is flawed for general use. Let's start with the edge case, the brute force long context dump. When do you allocate the massive compute budget required for Gemini 2.5 Pro?
The data dictates that you use it exclusively for singular, hyper-complex synthesis tasks.
Precisely. If your legal team needs to ingest the entire history of a multi-year corporate acquisition to find subtle contradictions between a 2019 term sheet and a 2023 email chain, you do not build a RAG system. RAG chunking will destroy the connective tissue.
Right.
You pay the high computational inference cost, you dump the entire 705,000 token corpus into the model's context window, and you allow the attention mechanism to map the entire data landscape simultaneously. It is slow, it is expensive, but it is structurally necessary for deep synthesis.
But the vast majority of enterprise queries are not massive synthesis tasks. They are pinpoint retrieval tasks. A developer needs an API key. An HR manager needs the exact wording of a compliance policy.
Which is where everyone defaults a RAG.
Exactly. The current industry consensus mandates building a production RAG system for this. Thomas's custom AskTom framework using text embedding 3 small is the exact blueprint being sold by enterprise vendors right now. Why is this not automatically the right answer?
Because the benchmark proves that RAG introduces a massive layer of unnecessary complexity that actively degrades accuracy for factual retrieval.
It only secured 2 wins out of 7.
Right. It introduces the risk of semantic blurring during embedding. It introduces the risk of fragmented context during chunking. And most dangerously, it introduces the high probability of fluent confabulation, the ElevenLabs hallucination.
Yeah.
If you need a system to reliably answer what is our standard server deployment protocol, a RAG system might overcomplicate the query, map the semantics incorrectly, retrieve an outdated protocol, and confidently present it as current fact.
Which directs us to the hidden champion of this experiment, the architecture that secured 5 out of 7 wins, the simple file and grep architecture, Karpathy's LLM wiki idea.
For standard organizational knowledge retrieval, the intranet, the employee handbook, the internal developer docs, maintaining your data in plain text markdown files, and deploying an AI agent armed with standard command line search tools is vastly superior.
It's highly transparent. You can inspect exactly how the data is structured.
It's computationally cheap to run locally. But above all, it fails safely.
It brings us to the central thesis of this entire deep dive. When evaluating an AI tool designed for knowledge retrieval, the absolute highest priority metric is faithfulness.
Faithfulness over fluency.
A system that adheres strictly to the literal characters on the page and possesses the architectural humility to halt and admit, I could not find the data, is functionally superior to a system that sounds incredibly confident while synthesizing a lie.
It is the necessary counter-movement to the current generative AI hype cycle.
But consider the reality of enterprise software procurement for a second. Let's be real. Executives love fluency. They're heavily influenced by polished demonstrations. A CEO wants an AI that feels like a science fiction movie. They want instant, smooth, comprehensive answers displayed on a sleek dashboard.
They do.
How does an engineering leader walk into a boardroom and successfully pitch a system that is literally a local folder of plain text files that will frequently reply with a clunky, search failed, 0 results found?
You reframe the conversation entirely. You do not attempt to sell the system on user experience or conversational magic. You sell the architecture purely on risk mitigation and liability reduction.
Interesting.
You bring the data from this benchmark into the boardroom. You highlight the RAG system fabricating the ElevenLabs shutdown, and you pose a direct scenario to the executive team. What is the quantifiable cost of this enterprise if our internal AI hallucinates a critical financial compliance metric while a vice president is preparing for an earnings call?
Or what is our legal exposure if the AI confabulates a safe protocol and an engineer acts on that false confidence?
Exactly. You weaponize the failure modes. You make the consequences of fluency tangible to the business. You establish that a highly confident, highly fluent AI is an active corporate liability if the retrieval architecture cannot guarantee absolute faithfulness to the source material.
A system that forces a search failed error acts as a hard operational guardrail. It forces human verification.
In high-stakes enterprise environments, rigid guardrails are exponentially more valuable than frictionless conversation.
Faithfulness over fluency. Risk mitigation over a slick user interface. It is a sobering but necessary perspective. Let's bring this narrative full circle and conclude Thomas Promer's Building My AI Twin project. Because this season 1 finale accomplished something remarkable. He systematically digitized himself layer by layer.
He established the audio layer with a highly accurate voice clone in episode 1. He established the visual layer, generating responsive video avatars in episode 2. And in this final episode, he successfully mapped the architecture required to clone his brain, his specific knowledge base, and the retrieval mechanics necessary to access it accurately.
And we absolutely must address the economics of this final layer because the data here provides a critical constraint on how we view AI research.
The financial efficiency of this benchmarking process is staggering.
I need to state this with absolute perfect clarity for you listeners analyzing your own budgets. The total compute cost for this specific second brain experiment executing the full 7-question battery across a custom or RAG pipeline, the Gemini long context dump, and the Claude Code file-based agent, as well as running the 5-turn working memory probe, was exactly $4.30.
$4.30 in API calls and token generation to comprehensively benchmark and evaluate the retrieval mechanics of his knowledge base.
And to ensure there is zero confusion regarding that metric, that $4.30 is the cost of this specific brain experiment only.
Right. It is strictly the cost of the text retrieval and memory evaluation we discussed today.
That figure does not represent the total budget for the entire Season 1 AI Twin project. Do not confuse the two. The audio engineering required to clone his voice in Episode 1 and the heavy rendering costs required to generate the video avatars in Episode 2 carried their own entirely separate, significantly larger financial requirements. Never let someone say it cost $4.30 for voice, face, body, and brain.
Exactly. Completely different scale.
But the raw architectural head-to-head battle for text retrieval. The compute required to prove that a markdown file beats a vector database. Just $4.30.
It dismantles the narrative that AI research is exclusively the domain of massive tech conglomerates with limitless budgets. It proves that rigorous, deeply revealing architectural experiments can be executed by individual developers utilizing systematic methodologies.
You do not need $1 million lab to expose the flaws in enterprise systems. You just need to hold your variables constant and question the marketing hype.
It's a masterclass in independent engineering validation.
It really is. And as we close out this deep dive, it leaves me with a final thought, something for you to ponder that extends beyond the specific technical merits of embedding models and chunking strategies. We have spent this entire session analyzing how a cutting-edge, highly engineered digital brain was comprehensively defeated by a boring, rudimentary folder of text files that simply knew its own limits and stuck to the facts.
The definitive triumph of a literal, unabstracted architecture.
Right. And what does that outcome reveal about how we organize our own cognitive processes? In our daily professional lives, are we prioritizing the confident, fluent delivery of a narrative over the boring, messy truth of the raw data?
That's a great question.
When confronted with a complex question in a meeting, do we act like the hallucinating Argo system, stitching together fragmented memories to formulate a response that merely sounds smart? Or do we possess the operational discipline of the file-based system, willing to halt the conversation and state clearly, I do not know the exact answer, let me locate the source file? In an era increasingly dominated by artificial fluency, perhaps the most valuable human trait is rigid, unyielding faithfulness to the truth. Until next time, keep digging.
Hello again. And that's a wrap on the Season 1 finale of CTAIO Labs. So there it is, voice, face, and now the brain. And the punchline still gets me. A folder of markdown files, navigated by a simple agent, beat the vector database 5 questions to 2. The lesson isn't never use RAG, it's that faithfulness. A system that can admit I don't know, beats fluency for a knowledge tool. And the whole thing cost $4.30. That closes Season 1. Building My AI Twin. Season 2 is agentic orchestration. I build the same agent in 6 different frameworks, pit 3 multi-agent topologies against each other in production, and put 4 agent observability tools to the test. Subscribe on Apple Podcasts, Spotify, or YouTube so you don't miss it. And if this was worth your time, share it with someone who's building in this space. I'm Thomas Palmer. This is CTAIO Labs. See you in Season 2.